Hello everyone, let's now look at the last practice problem for chapter 9. To test the effectiveness of an anti-plaque radiance on plaque buildup, 7 people each were selected for a control group. And an experimental group that received an anti-plaque radiance. After 14 days, the control group had an average of 1.26 plaque index with a standard deviation of 0.32. The experimental group had an average of 0.78 plaque index with a standard deviation of 0.28. At alpha equals 0.1, its radiance performed better. And I think it's a typo. There should be another condition here. Let's just fix that very quick. So let's say assume equal population variance. Okay, that's the question. So now we can kind of just highlight the important information. So 7 people each were selected. We have a control group and an experimental group. So we have x1 bar, standard deviation, x2 bar, standard deviation, alpha equals 0.1, better, that's the direction for the claim, and then we assume equal population variance. Those are all important information. So now we need to list the known information. Okay, so we first gonna state the group. So let's say group 1 that's the experimental group. And group 2, that's the control group. And then we have N1 for the experimental group. The sample size N1 is 7, x1 bar. .78, right? For the experimental group, average is 0.78. Sample standard deviation equals 0.28. And then for the control group, N2 equals 7, x2 bar equals 0.38, x2 bar equals 1.26. And then S2 equals 0.32. And assume population variance, they're equal, and we're given the sample information. So sigma 1, sigma 2 unknown. Of course, this is for the 2 sample case. Sigma 1, sigma 2 unknown. And then assume sigma 1 equals sigma 2. Okay, then we can start our 5 steps. And again, you can check the 2 sample table for the steps. For this one, let's just do it all together. Step 1, state the hypothesis. We have the null, always mu1 minus mu2 equals 0, or mu1 equals mu2, either way is fine. And then for the alternative hypothesis, so mu1 minus mu2, what? 0, right? So then we have to look at the claim. Is Rayans perform better? So when we say Rayans perform better and the data represent the Planck index, that means Rayans should have lower Planck index. So then if group 1 means Rayans, group 2 means no Rayans, the Planck index for group 1 should be smaller than the Planck index for group 2, right? So although it says better, but based on the group setup, 1 represent experimental group, 2 represent control group. So we say the alternative hypothesis is a smaller than sign. So it's less than. So that's why we always specify the groups at the beginning. So we need to label which one is group 1 and which one is group 2 so that we have the correct sign for the alternative hypothesis. Even though it says better, it is smaller than. And then after we know that, we can look at our step 2, critical value. So the critical value is determined by the sign, smaller than, and alpha. And also sigma 1, sigma 2 unknown. And assume sigma 1 equals sigma 2. So from that smaller than sign, we know is the critical value, we have a negative sign. We call it one tail left, right? We have a negative sign. And sigma 1, sigma 2 unknown, so we know we have a t distribution. And then alpha, one tail left, so we have t sub alpha, right? So from that, we know the degree of freedom equals n1 plus n2 minus 2. So then altogether, the critical value is negative t sub alpha with df equals n1 plus n2 minus 2. So go back, alpha equals 0.1. So we're checking negative t sub 0.1 with df equals n1, that's 7, n2, that's 7. So 7 plus 7 minus 2, that's 12. So we need to check the table, the t-table, to get that. So after we check the t-table, we got 1.356. Don't forget we have a negative sign in front. So negative 1.356 is the critical value. Good for this step too, but if you want to specify the rejection region, you can write that down. So we're going to reject H naught if the later calculated test statistic is smaller than negative 1.34356. So then step 3, we want to calculate the test statistic. So t equals x1 bar minus x2 bar over square root of sp squared over n1 plus sp squared over n2. So we need sp, right? So that's square root of n1 minus 1 s1 squared plus n2 minus 1 s2 squared divided by n1 plus n2 minus 2. So plug in, right? So n1, that's 7 minus 1 times s1 squared as 1.28. 0.28 squared plus 7 minus 1 times 0.32 squared, and divided by 7 plus 7 minus 2. So let's use the calculator to calculate it out. Square root of 6 times 0.28 squared plus 6 times 0.32 squared, and divided by 12. And then don't forget to take the square root, 0.3. So then we have the test, the pole standard deviation, SP equals 0.3. And then we can just plug in, calculate the test statistic. X1 bar, 0.78, 1.26. Square root of 0.3 squared over 7 plus 0.3 squared over 7. So we're going to use the calculator. Again, don't forget the parentheses. 0.78 minus 1.26 divided by root of 0.3 squared over 7. So negative 2.99. That's our test statistic. Then we can look at step 4. Decision, right? Write on the test statistic. And then the sign is smaller than. Write that down, and then write the critical value. So it is, right? We want to see the test statistics even smaller than the negative side of the critical value. That means more extreme, right? It is. So we reject the null hypothesis H naught. And step 5. There is enough evidence to conclude reins perform better at alpha equals 0.1. That's our conclusion. Okay, then we finished the 5 steps for this practice problem. Thanks for watching.